Let's look at some more examples. Okay, so let's look at Z mod 5Z under addition and multiplication. Does it form a ring? Now remember, Z mod 5Z is going to be 0, 1, 2, 3, 4. Yes, the remainders. That means dividing what? Dividing any integers. Okay, so let's look at whether it forms a ring. And as usual, I will put up the checklist, right? So that I don't miss out anything. Okay, so let's look at the first one, closed under addition. Remember, we have to take an arbitrary number, arbitrary element, add it with another element, and see whether the resultant is also belonging to that structure. So we know 2 plus 3 is equal to what? 3 plus 2 when divided by 5 gives us 0. Similarly, 3 plus 4, 7. So when divided by 5 gives us remainder 2. And this belongs to R. This belongs to R. So let us say this entire thing is R. Okay. Similarly, you can try out some values or you can keep it general is equal to 0, which also belongs to R. So it is closed under addition. So now let's look at the second one. Okay, so associative under addition. So let's see 2 plus 3 plus say 4. If we take these two first, does it equal to 2 plus 3 plus 4, right? And let's actually do it. This will be 5, 3 plus 2 is 5, which will be 0 plus 4 is equal to 2 plus 3 plus 4 is 7. So this will be 2. 0 plus 4 is 4. 4 divided by 5, remainder is 4. Here 2 plus 2, 4. So divided by 5, remainder is 4. This, so they are the same. So it is associative under addition. Now additive identity. So additive identity is 0. Is the additive identity. Let's put it like this. Right? So which means what? If we take any element, say 3, and we add 0, what do we get? We again get, and same way if we take it in the other direction, this would also be 3. Okay, now let's look at the fourth one. So we have taken care of additive identity. Now additive inverse. So what will be the additive inverse of 0? It's 0, right? Since 0 plus 0 is equal to 0. Remember, when we add these two element and its inverse, we should get the identity, that is 0. So which means what? Inverse of 1 is going to be 4. Since 1 plus 4 is equal to 5, mod 5 is 0. Similarly, 2 inverse is 3. So 2 plus 3 is equal to 5, which is mod 5 is 0. Again, 3 inverse is 2. So 3 plus 2 is equal to 0. And finally, 4 inverse is 1. So 4 plus 1 is equal to 0. So an inverse exists for each of the elements, additive inverse. Okay, so that takes care of our next condition. Now addition is commutative. So again, let's take any two elements. 3 plus 2 is equal to 2 plus 3. In both the cases, it comes to 5. So 5 mod 5 is 0. Or in other words, in this case, we can write it as an arbitrary element x plus n minus x is equal to 0. So if you have an element, its inverse is n minus x. What is the next one? Addition is commutative, we have taken. Closed under multiplication. So again, let's take some examples to, because it is a very small set, we can actually do it. So times 3, 3 times 2 is 6, 6 mod 5 is 1, which belongs to R. Similarly, 3, 4, 3 fours 12, 12 mod 5 is 2, which belongs to R. 1 times 4. 4 ones 4 is 4. So 4 mod 5 is 4, which also belongs to R, right? So it is closed under multiplication. Now associative under multiplication. So let's look at that. So let's again take some examples. 2, 3 times 4. Let's do this, and this should come out to be the same as 3 times 4. So what will this be? 3 times 2 is 6. 6 mod 5 is 1. 4. 2 times 3 fours 12. 12 mod 5 is 2. Here again 4 ones 4. 4 mod 5 is 4. 2 times 2 is 4. 4 mod 5 is 4. So it is associative under multiplication. Now let's look at the next condition. So it is associative under multiplication. Multiplicative identity exists. Now does it? Now the multiplicative identity is 1. Is the multiplicative identity. And you can verify this very quickly by creating a table. Now remember, you can't put 0. So put the remaining ones. 1, 2, 3, 4. Okay, multiplication mod 5. So 1 times 1 is 1, 2, 3, 4, 2, 3, 4. 2 times 2 is 4, 4 mod 5 is 4. 3 times 2 is 6, 6 mod 5 is 1. 4 2 is 8, mod 5 is 3. 3 2 6, 6 mod 5 is 1. 3 times 3 is 9, 9 mod 5 is 4. 3 4 is 12, 12 mod 5 is 2. 4 2 is 8, 8 mod 5 is 3. 4 3 is 12, 2. And 4 4 16 is 1. So if you notice, 1 is there in every row. Okay, so that means 1 is a multiplicative identity. And finally, we have to look at multiplicative identity exists. Yes, multiplication distributes over addition. Okay, so that is what we have to look at now. So let's take 3 times 2 plus 4 is equal to 3 times 2 plus 3 times 4. So this implies 3 times 4 plus 2 is 6. 6 mod 5 is 1. 3 times 2 is 6. 6 mod 5 is 1. Plus 3 fours 12. 12 mod 5 is 2. Okay. This is 3 times 1. So 3. 2 plus 1 is 3. So it is distributive. So which means it is a ring. So that is 1. Now let's look at the second example. Polynomial ring. So basically what we have is a polynomial in X where the coefficients are real numbers. Okay, so x to the power of n plus a n minus 1 x n minus 1 plus a n minus 2 x n minus 2 and so on till a1 x plus a naught, where ai belong to the set of real numbers. Okay, so let us say our ring is R of real polynomials under addition and multiplication. Okay, again what we have to do is checklist. Now closed under multiplication, remember we can write it as functions of x. So before I start off with individual, let's define certain terms. F of x, one of the polynomial, is, let us say, x square plus 2x. I'm going to purposely keep it simple because otherwise it tends to, when we multiply, it becomes unwieldy. So g of x is equal to 2x plus 1. H of x is equal to, let us say, x cubed, just to keep it simple. You could always take with more terms. Okay, now let's look at closed under addition. What does this mean? We take any two polynomials. If we add them, we should get another polynomial which is in this ring. So let's do this. What do we get? X square plus 2x plus 2x plus 1, which is equal to x square plus 4x plus 1. So this belongs to our, you can take any this one. So you could take g of x plus h of x. This should belong to R. So which means 2x plus 1 plus x cube, which is nothing but x cube plus 2x plus 1, which belongs to R. So it is closed under addition. Associative. So here we will require all the three. So let's take f of x plus g of x plus h of x. Let's take these two first, and then let's take f of x plus g of x plus h of x, and let's do this here. So what do we get? This implies f of x is x square plus 2x. So x square plus 2x plus g of x is 2x plus 1 plus h of x is x cube. This should be equal to x square plus 2x plus g of x is 2x plus 1 plus x, which implies this will be x square plus 4x plus 1 plus x cube equal to x square plus 2x plus 2x plus 1 plus x cube, right? So this becomes x cube plus x square plus 4x plus 1 is equal to x square plus 2x is 4x. Let's start with x cube plus x square plus 4x plus 1. So both are equal. So it is associative under addition. Additive identity exists. So 0 is the additive identity. So which basically means f of x plus 0 is equal to, remember 0 is also a polynomial, right? So 0 is equal to f of x, or g of x equal to plus 0 is equal to g of x. So additive identity is 0. Then what? Next is additive inverse exists. So there exists an element minus f of x such that f of x plus minus f of x is equal to 0, which is the additive identity. So here f of x is not the specific polynomial. This is a generic polynomial, an arbitrary polynomial. So if you take the minus of that, you get the additive inverse. So for example, if we take this itself, let's say uh, g of x. So g of x plus minus g of x is equal to 0. And you could actually take an example plus minus 2x plus 1 equal to 0. So 2x plus 1 minus 2x minus 1 equal to 0. So, right? Okay, so fifth one. So we have a additive inverse. Now addition is commutative. So that means f of x plus g of x should be equal to g of x plus f of x. Again, we can use the same x square plus 2x plus 2x plus 1 should be equal to 2x plus 1 plus x square plus 2x. We could actually, keep it general and use n, a n, x n and do this, but it becomes a little bit tedious. So I'm just using some examples and doing this. So x square plus 4x plus 1 is equal to x square plus 4x plus 1. So therefore, it is commutative under addition. Now closed under multiplication, f of x times g of x should also belong to R. Okay, so let's take the example x square plus 2x times 2x plus 1 should also belong to R. So this would be what? 2x cube plus x square plus 4x square plus 2x, which implies 2x cube plus 5x square plus 3x. And this belongs to R. So therefore it is closed under multiplication. Associative under multiplication. Seventh one, f of x times g of x times h of x is equal to, and this is going to become tedious. So let's say we take it first here and then we do. Okay. Now here f of x is x square plus 2x times 2x plus 1 times x cube. This should be equal to x square plus 2x, g of x is 2x plus 1 times x cube. So this implies, let's multiply this, 2x cube plus x square plus 4x square plus 2x times x cube is equal to x square plus 2x, and this would be 2x4 plus x cube, which implies this will be 2x6 plus x5 plus 4x5 plus 2x4. I should have added these two. Okay, no problem. Now this would be 2x6 plus x5 plus 4x5 plus 2x4. So what do we get? 2x6 plus 5x5 plus 2x4 is equal to 2x6 plus 5x4 x5 plus 2x4. Both the sides are equal. So it is associative under multiplication. Multiplicative identity exists. So what is the multiplicative identity of this structure? So multiplicative identity is 1 is the multiplicative identity. So which means 1 times f of x is equal to f of x times 1 equal to f of x. Okay, so this is pretty straightforward. Multiplication distributes over addition. So 9 1. So let's take that. We have, let me actually write it, f of x times g of x plus h of x is equal to f of x times g of x plus f of x times h of x. Now here, what do we have? X square plus 2x times g of x is 2x plus 1 plus x cube. Now this should be equal to x square plus 2x times 2x plus 1 plus x square plus 2x times x cube. Okay, so let's do it. X square plus 2x times x cube plus 2x plus 1 is equal to, now, 2x cube plus x square plus 4x square plus 2x plus x5 plus 2x4, x to the power of 5 plus 2x cube plus x square plus 2x4 plus 4x square plus 2x is equal to 2x cube plus x square plus 4x square is 5x square plus 2x plus x to the power of 5 plus 2x to the power of 4. Let's arrange it and simplify it. So x to the power of 5 plus 2x to the power of 4 plus 2x cube plus 5x square plus 2x is equal to x to the power of 5 plus 2x4 plus 2x cube plus 5x square plus 2x, and they both are equal. So it is satisfying this condition as well. So therefore R is a ring where R is equal to the set of all polynomials with real coefficients under addition and multiplication. Okay, so that is another set of examples. That's it for now.